Section 5.3 Binomial Probability Distributions. Consider the following scenario. Children are playing a dart game at a carnival. If the dart lands in the blue area of the board, they win a stuffed animal. Otherwise, they do not win a prize. Blue areas make up 20% of the dartboard area. What is the probability that of the next 10 children who play, exactly 2 will win a stuffed animal? This type of problem is typical of a binomial experiment characterized by having only 2 possible outcomes: land on blue or do not land on blue. Beyond having 2 possible outcomes, all binomial experiments must have the following properties. Now, this is very important when determining if an experiment is a binomial experiment. All 4 of these properties have to be met, not just 2 of them or 3 of them, but all 4. And here they are. Number 1, there are a finite number of trials. So there has to be a stopping point that you can count. We don't want something that continues on and on and on forever, but a countable number of trials, 10, 15, 100, 1,000, however many. We call the number of trials n. So n represents how many trials we have. 2, the trials are independent. And we've heard this word before. That means what happens on the first trial has no effect on what happens on the second trial or the third trial and so forth. So all the trials are independent of each other. Number 3, each trial has only 2 possible outcomes: a success or a failure. And depending on the context of the problem, that could be yes or no, or some other two possible outcomes, but we boil it down to success or failure. And number 4, the probability of success must remain the same from trial to trial. So this is similar to sampling with replacement, when each trial is going to start off with the same arrangement, the same possibility of getting an outcome. So the probability of success has to be the same from trial to trial. So taking into consideration the 4 properties of a binomial experiment, let's verify that the carnival problem satisfies the properties of a binomial experiment. So number 1, there are a finite number of trials. Well, yeah, there are, because there are 10 children who will play. So we're not talking about every child who has ever played. That will, or who will ever play. That would be infinite, because it just keeps going on and on and on. But we're talking about just 10 kids, so that's definitely finite. It meets that property. Number 2, the trials are independent. Yes. Each child's play is independent. What one child does, whether they win a stuffed animal or not, has nothing to do with what the next child will do. Number 3, each trial has only 2 possible outcomes. True. Either you land on blue or you don't land on blue, so that's true. So either the child lands on blue or not, so that fits. And finally, 4, the probability of success is the same from trial to trial. Now here we're not depending on the child itself, meaning whether it's an older kid versus a younger kid, or someone who has experience throwing darts versus someone who's a complete novice. We're not basing it on that. The probability of success, meaning the board is going to stay exactly the same for every kid. 20% of the dartboard area is blue, and they all have the same probability of making it into the blue area. But we're not basing it on skill. But so here we will say the dartboard stays the same. Okay, so definitely fits all 4 characteristics or properties of a binomial experiment. Well, let's set out to try to find the probability that 2 children will win. First, we need to take into consideration that now we know the probability that someone wins is 20% because of the 20% blue area on the dartboard. But we also want to take into consideration that if 2 kids win, 8 kids will not. So if we think of this using the fundamental counting principle that we talked about in Chapter 4, think of having 10 slots. So let's say the first 2 kids win. What's the probability that each one wins? 0.2. Well, the next 8 kids will not win, and the probability that they will not win, if we do 1 minus 0.2, is 0.8. So we can write that a little bit neater, clean that up and say 0.2 raised to the second and 0.8 raised to the 8th. Let's see what that gives us. So I get 0.0067. Now on my paper I'm just going to write down 4 places, but in my calculator the number was much longer. When I do another calculation I'm going to use the calculator number, so just be careful of that, not to round too many of the intermediate steps. Okay, now the 0.0067 only represents the probability that 2 kids win in this exact arrangement where the first 2 win and the next 8 don't. But we have to think about all the different ways that 2 kids can win. What if it's the first kid and the 10th kid that wins? Or the 5th one and the 7th one that win? All those different arrangements have not been taken into consideration. And in order to do that, that requires a combination, because we're interested in, out of 10 kids, how many will win, and we don't care of the 2 which one won first. We're only interested that 2 kids win. So it's not a permutation. We're not worried about the order of the 2 who win, just that we get 2 kids that win. So if I want to set this up as a combination, I would say 10, choose 2, and using our formula, that'd be 10 factorial over 10 minus 2 factorial and then 2 factorial. If we simplify a little bit, that would be 8 factorial times 2 factorial. And we learned about, you can do this by hand or you can do it in your calculator. I can factor out the 10 and the 9 and then stop at the 8 factorial, because then those 2 will cancel out. So then I have 90 divided by 2, which is 45. You could also do this in your calculator with the, if you touch your or hit your math button, go over to PRB, and then number 3 should be your NCR. And recall to enter it, you type your 10 into your calculator first, then go get your NCR button, and then type in the 2, and you would get 45 just as well. Okay, so now we know that there are 45 different ways that two kids can win, either the first and the second, or the last 2, or the middle 2, or the second and the 8th, or any of those different combinations. There's 45 ways that that can happen. So to get the true probability that any 2 kids can win, I'm going to take the 45 ways that it can happen, multiply it by 0.0067, which is the probability of just one way that it can happen. And in my calculator, I'm going to do the multiplication. Remember, let your calculator handle that, all the decimal places that came afterwards for accuracy. And I get 0.302 if you round to the 3rd place after the decimal. So 0.302 represents the total probability of exactly 2 children winning. So we couldn't just say multiply the probabilities of 2 kids by 8 kids losing. We had to take into consideration all the different ways that that could happen, and we got 0.302. Well, of course, I mean, this was doable, but of course we want a simple way to determine the probability if we decide to change the number of children who win. or we might change the number of children who play. So that leads us to the binomial probability formula. Okay, so the probability of X successes, so the positive outcomes I want to happen, out of n trials with probability of success P and probability of failure Q, and remember Q is the complement of P, so that's just 1 minus P, is given by this formula. Now don't let this be too intimidating. This part here, this n factorial, n minus x factorial, that's just your NCR. And if you prefer to write it that way, that's perfectly okay. That's your combination portion of the binomial formula. Then here you have p to the x. Well, this is the probability of a success raised to the number of successes we have. So, like in our example, we had 2 kids, so we had 0.2 twice, raised to the second power. Then q is the probability of failure raised to the n minus x. Well, remember, n is the number of trials and x is the number of successes. So the difference between the two gives us the number of failures. And just like in our example, we had 10 kids playing, 2 who were going to win. So 10 minus 2 gave us the 8 who were not going to win. So that's your probability, your binomial probability formula. Let's try that out here. So example 1, the directions here are just basically saying you have a valid probability distribution. And they're telling you in each one how many trials, the number of successes, and the probability of a success. So let's take a look at A. If I were to set this up, I could say 6 for n, choose 1. So out of 6 trials, I want 1 success. The probability of a success is 0.25, and that's only going to happen once. But the probability of a failure is 0.75, 1 minus 0.25, and out of the 6 trials, that's going to happen 5 times. So I can put that all in my calculator. Remember to type in your 6 first before you go get your NCR function in your calculator. And I am getting 0.356 if you round to the nearest, or round to 3 places after the decimal. Okay, try B. So we have 12, choose 10. So X is 10, the number of successes. And so the number of successes, and we want 10 of those. The probability of a failure is 1 minus 0.8, so 0.2. And we'll raise that to the second. So if there's 10 successes out of 12, there's only going to be 2 failures. And let's see what we come up with for that. And I'm getting 0.2834, 35. Okay, in this last one, I'm going to change this probability to 0.4 instead of 0.04, just so our numbers don't get so weird. So we have n trials, but we have n successes. So I have 8C8.4 raised to the 8th power, and 0.6, so probability of a failure. Well, if all the trials are going to be successes, that means I have 0 failures. So that comes out to, well, you're probably getting something like this, 6.5536e to the -4th. Remember, that's just scientific notation. That means move your decimal 4 places to the left. So this would be that if you wrote it all out. Okay, so hopefully that gave you a little bit of practice with just setting up the binomial formula, typing it into your calculator. Certainly for each of these, you could have also done the factorial notation, so 6 minus 1, and then 1 factorial, and cancel Except 6 factorial, 5 factorial, 1 factorial, and done all of that. But most of our calculators are pretty savvy that we can just type in the combination numbers to get that part. Okay, let's try this out on a word problem. Central Eye Clinic advertises that 90% of its patients approved for LASIK surgery to correct vision problems have successful surgeries. Find the probability that of the next 15 patients approved for LASIK surgery, 12 of them will have successful surgeries. First, let's just make sure that this fits a binomial experiment. We have those 4 properties, and which one you verify first doesn't matter, but let's just go through and make sure this fits. First, I need to know that I have finite trials. Well, I do. I have 15 patients. This isn't how, the number of patients over years and years and years. So 15 patients, that works. Are the trials independent? Well, one patient's success with the surgery is completely independent, has nothing to do with another patient's surgery. So we know that they're independent. Are there only 2 possible outcomes? Yes, either the surgery is successful or it's not, so that fits. And finally, is the probability of success the same from trial to trial? We're just using the 90% as in this is what has happened in the past. So we're going to use that as our probability. We're not basing it on the patient itself, but just that if we took a random patient, what's the probability that the surgery is successful? So that's also the same. So this definitely fits for being a binomial experiment. Let's see what we have here. We have the number of trials is going to be 15 since 15 patients were approved. So I can say 15 choose, and we're interested in that 12 of them will be successful. The probability of a success is 0.9, and I want 12 of those to be successes. And the probability of not being successful would be 1 minus 0.9 or 0.1, and we're saying that the other 3 will not. So let's see what happens there. And I'm getting 0.1285. So the probability that 12 of them will have successful surgeries is 0.12. Okay, and be careful here. This probability represents that exactly 12 of them will have successful surgeries, not 12 or more than 12 or less than 12. It's just exactly 12. So about 0.12 or 12%. Example 3. A statistics student who didn't study for an exam decides he is just going to randomly guess on each multiple choice question. If there are 5 possible answers for each of 12 questions, determine the following probabilities. Now with this problem, we have a little bit more work to do. In the previous problem, we were given a probability or a percentage to use. Here we have to figure out what the probability of a success will be. Well, if there are 5 possible answers, only one of them is going to be right. So the probability of success is 1 out of 5 or 0.2. So we have to find that first. Now we're interested in a few different things. A, what's the probability he will get exactly 8 questions right? Let's see. So probability that X equals 8. So we're going to set up out of 12 questions or trials, there are 8 that we're interested in being correct or successful. So those, the probability of getting it right is 0.2. We want 8 of those. But the probability of getting it wrong is 0.8, and we are going to have 4 of those. Let's see what his chances are. Pretty small. You're probably getting something like this on your calculator. Remember that means move your decimal 4 places to the right. So it's a pretty small chance that he's going to get exactly 8 questions right. Let's take a look at B. What's the probability that he will get at least 5 questions correct? Well, that means the probability that it's 5 plus the probability that it could be 6 or 7 or 8 or 9 or 10 or 11 or 12, which means we would add up all of those individual probabilities. Just for the sake of calculations on this problem, let's change this. I didn't realize that was going to be so much work. Let's change this to 10. He will get at least 10 questions right, because that's a lot of work to do. So at least 10 would mean the probability that x equals 10, or the probability that x equals 11, or the probability that x equals 12. So what that means is I have to find the probability, binomial probability for each one, for 10 and for 11 and for 12. So here I would set up 12, choose 10, 0.2 to the 10th, 0.8 to the second for the 2 leftovers that are not successes. Then I would say 12, choose 11, 0.2 to the 11th, 0.8 to the first, and then 12, choose 12, because I want to get all of them right, 0.2 to the 12th, 0.8 to the 0. So let's find each of those. So for that first one, I get 0.43 e to the negative 6, which is that scientific notation. So if I move my decimal place over 6 times, a really, really small number. And then for the next one, I get another very tiny number. And for the last one, an even smaller number. So it's not looking too good that he's going to get at least 10 questions correct. So if we add all of those up, I get 0.12, there's 5 zeros, 0.45. So the probability that he's going to get at least 10 questions correct just by guessing, really, really small. But the point I wanted to illustrate here is for at least, we're taking the number 10, but also saying he could have gotten 11 correct or 12 correct, and we're going to sum up all those probabilities, but I had to find a binomial probability for each one separately and then add them up. In like fashion for C, the probability that he will get at most 3 questions correct, well, 3 is the most he can get correct, so we're saying, well, he could also only get 2 right, or he could only get 1 right, or he could even get none of them right. So we're going to add up all of those individual probabilities. So for this first one, I would set up 12C3, 0.2 to the third for the number that he gets right, 0.8 to the 9th for the ones that he gets wrong, and then 12C2, 0.2 to the second for the ones he gets right, 0.8 to the 10th for the ones he gets wrong, and then 12C1, 0.2 to the first for the one he gets right, 0.8 to the 11th for the ones he gets wrong, and then finally 12C12, 0.2 to the 0, he gets none of them right, and 0.8 to the 12th. Let's see what we get. So for 0, I have 0.06872 is that probability that he gets none of them right. that he gets one of them right, 0.20616, that he gets two of them right, 0.28347, and that he gets three of them right, 0.23622. And then I'm going to add all of those up together. Which is 0.79457. So it's very likely that he'd get just 3 or 2 or 1 or none right, whereas it's highly unlikely that he would get 10 or more correct. So in each case, with the at least or at most, really think about what direction are you on it. Is it this number and more, or this number and less? Really think about that. And then you have to set up a binomial equation for each individual probability and sum them all together. Be sure to take a look at the video for entering this in your calculator, and you'll see how you can do this quite a bit faster.